Hello friends, let's now discuss another type of governor that is called as Hartnell governor. So it's a spring-loaded type of governor. You can see the image of the Hartnell governor over here. In this, the fly balls are mounted on two bell crank levers, and these bell crank lever are attached to the spindle axis, the arm on the spindle axis at this fulcrum point. The other end of the bell crank lever will have rollers which will roll on the sleeve. So let's see the construction details. So this is the construction diagram. So if you see, there is a spring along the spindle. This is a sleeve. These are two bell crank levers. The fly balls of mass M are attached, and this is a sleeve and roller. This spring will have the initial compression. So that is a construction of Hartnell governor. Let's say its force analysis. So for this we consider some position, we call it as position 1 of the bell crank lever. So this CAB is a position of bell crank, and we have drawn the free body diagram at that position. Fly ball will be here at the radius R1. So if you see, it is inclined inwards. So we can also say that this is a position of minimum speed. So forces acting on this bell crank lever at this position are the centrifugal force F1, and that is equal to mR1 omega 1 square. The omega 1 is a speed with which the governor is rotating bell crank lever at position 1. Next force acting will be the weight of the fly ball, which is mg, and it will be acting downwards. The next force will be acting at the sleeve end, and it will be capital Mg plus Fs. Now Fs is a notation used for the spring force, plus F, that is a force of friction, and divided by 2 as we are only considering the one side of the governor. So the half force is taken. So this is a free body diagram and the forces acting on the bell crank lever. Now what we will do is, we will try to take the moment about this fulcrum point A, which will give us the equation F1 A1, this distance is A1. So F1 into A1 is equal to mg into C1 plus 1 by 2 into bracket mg plus fs1 plus f, and it is situated at the distance b1 from the fulcrum A. The notation used here is capital F is for centrifugal force, and capital F subscript S is used for spring force, whereas the numerical subscripts correspond to the position. So this is for position 1. Next what we do is, we again consider the free body diagram at position 2. So what is the difference between position 1 and position 2? At position 1, this fly ball was inclined, this link CA or portion CA of the bell crank was inclined inside, whereas it is inclined outside. So here obviously the speed of the governor will be more than that of position 1. We can also consider it to be the maximum speed. Sleeve has moved upwards since the position 1, and the speed at this position is omega 2. Forces acting will be the same, not the value, but the type of forces acting will be same. Centrifugal force, which value would have changed to mR2 omega 2 square, and mg plus only the spring force will change, fs2 plus f, and divided by 2. These distances will also change, that is b2, a2 and c2. So again same thing we are going to do. We are going to take moment about fulcrum A. So it will give us the equation F2A2 is equal to mgc2 plus 1 by 2 into bracket capital Mg plus fs2 plus f into b2. Okay, now we'll try to consider both these equations together. So these are the equations we arrived at by taking the moment balance about fulcrum A for position 1 and position 2. Next we will make one small assumption that theta is very small. What is theta? Theta is the angle travelled by the bell crank lever from position 1 to position 2. So this is theta. So we assume it to be very small. So what difference does it make? We see that the distance A1 is equal to A2 and then we'll call it simply A. Also B1 and B2 are equal and we'll call it simply B. Whereas C1 and C2 will become 0. Since theta is small, C1 and C2 we can say that they are 0. So substituting this into these two equations, our equation will get modified. So we will drop the subscripts of the distances and put the value of C as 0. So our equation get modified. Now we will try to subtract these equations. So subtracting, we get F2 minus F1 into A is equal to 1 by 2 into bracket Fs2 minus Fs, here it should be Fs1, sorry for the typo. So the equation will be F2 minus F1 into A is equal to 1 by 2 into Fs2 minus Fs1 times B. Rearranging, I can alternatively also state that Fs2 minus Fs1 is equal to 2A by B into F2 minus F1. Next, what we will do is, suppose now stiffness of our spring is Ks and H is the total moment of your sleeve. So from going to position 2 from position 1, the total moment of the sleeve, that is vertical moment, will be H. Let's assume that it is H. So therefore, the spring force, the difference of the spring force will correspond to stiffness multiplied by the moment of the sleeve. Next, I substitute it into the equation we concluded on the last slide. But also, the value of H is equal to theta times B and the value of theta will be R2 minus R1 by A. I will shortly explain how we arrive at this. So this is position 1 and so this is position 2. Now this is your theta and this is also theta and this distance is B and the distance travelled by the sleeve, this is H. So approximately, since theta being small, the length of this arc is equal to H and that is equal to theta B. Again, now this distance from the spindle axis is R1 and similarly this distance is R2. So length of this arc is R2 minus R1, which will be equal to, now this radius or this distance is A times theta. So the value of theta will be R2 minus R1 divided by A. So combining these two, I will get the value of H as B by A into bracket R2 minus R1, which I will substitute into this equation. So it will be Ks into bracket B by A R2 minus R1 is equal to 2A by B F2 minus F1. So we'll just rearrange the terms and arrive at the final equation, that is stiffness of the spring is equal to 2 into A by B squared into another bracket F2 minus F1 divided by R2 minus R1. So that's our conclusion of force analysis of Hartnell governor.